Hello, students. Good day. I hope all of you are good and looking enthusiastically towards learning more about operating systems. The topic of today's discussion is process management. In this topic, we will learn about how processes are managed in an operating system, what are the different stages a process goes through during its life cycle, what are the basic terminologies that are used in the operating system, what do we mean by task, process, program, a job, what is the difference between quite common terminologies that we use quite frequently in systems. So let's begin today's lecture. So over here we have a set of important terminologies that one should be able to distinguish after completing this course. The first terminology is task. Uh, a task is any program that is stored on the hard disk. Before you double click onto some program, or if you are entering some command from the console, so before pressing that enter key, you call something as a task. It is not yet becoming a process, a full-fledged process, but it's just a task that may be valid or invalid within the special settings or within the special privileges assigned to the user. So before you double click on it, it is just a task. The second important terminology is job. So when you actually double click on a program or you press the enter key, your operating system analyzes from the set of available tasks whether this job is a legitimate job or not. So whether it should be submitted to the operating system for further processing, whether whatever resources we have or whatever resources this program is asking or requesting from the operating system, should we let those resources to be assigned to this program. So all of this checking is done. uh, Whenever we are doing this checking, we call a particular program just as a job. So when it is just installed, it is just a task. When we submit it to the operating system, and operating system validates its working or validates its legitimacy, at that moment it is a job. And once operating system confirms that this can be executed, it becomes a process. So this process is the third important terminology. So at this time a job is assigned all the resources that it is requesting. It is loaded onto the memory, and all the IO that it requests are allocated to it, and it is again processed to further execution. So over here we have an example. So for example, all of you may be aware of dir command. So that is used to represent a list of directories or list of folders that are there onto that particular folder. So for example, when you write down dir, at that moment it is just a task. So when you press the enter key, this task is submitted to the operating system, and operating system checks its validity, whether the command is a legitimate command, or maybe if in case of some misspelled word, then operating system will say that this is not a valid command. It checks it from the list of legitimate uh, tasks that it can perform, and then it either verifies it or rejects it. So if it verifies it, uh, then it becomes a process. This particular job is loaded onto the main memory, and all the resources that are requested or required by this process are given to it. So for example, we have for example, if I ask you to do a particular assignment. So now you have two choices, whether you will take up this responsibility or you will ignore it altogether. So when I am assigning it to you, it's just a task for you. So now it is up to you whether you make it become your job or you let it ignore altogether. So it was a task. Then, if you realize that now you should do it because you want good grades or you want to understand the concepts lying behind these things, then it becomes a task or a job for you. A task becomes a job when you select, when you realize that it's a valid thing to do. Once you start doing it, it becomes a process. We have task, it becomes a job, and then it becomes a process. So when we are in this process management, we often use this word process. Process is just a program, but it is in execution. So during the execution of a uh, program, we call it the process. When we talk about systems, this process is the basic unit of work. So we may say that this particular operating system or this particular scenario has multiple processes running into it. We means that one process is an autonomous unit, and it's a unit of work within the system. Usually when a program is stored onto the hard disk, it is not consuming any resources. So it's just a passive entity that is stored, that is lying there in the system. When we initiate it, when we load it, or when we just try to execute it, it becomes a process. Now it's an active entity. Now it demands some resources, including the memory space, including the execution time from the CPU, including certain I/O devices. And then when it is in the system, then there are several other stuff that are associated with it. And we will talk about all of them in detail. This subject of operating system revolves around process. So throughout this course, we are only concerned about how a particular process can be executed. Like for example, when it is in the processor, what are the stages it will go through, how the how a processor will manage multiple processes, what will happen if two processes they are having contention for a single device or single resource, as well as what will happen when you load a process onto your RAM. So all of this course revolves around this entity of process. So this is fairly important that you understand it, that a program is a passive entity that is just stored on your hard disk. When it becomes process, it's an active entity that demands all the resources. And you know I hope you remember that from the basic definition of operating system. One of the basic definition or role of the operating system is to facilitate the execution of user processes. So again, the whole course revolves around the execution of process. Usually, when we talk about process, we claim that a process requires some resources to complete its task, complete its job. And those resources may include the CPU time, memory, I/O devices, files, and it has some data associated with it. When a process is in execution, it requires all of the resources required to complete its job. However, when a particular process completes its execution, it is terminated, and all the resources that were initially allocated to this process, they are reclaimed by the operating system. So that is how operating system reuse the resources and allocate it and reallocate them to multiple processes. Usually, there are two types of processes. One is single threaded processes and the other ones are multi-threaded processes. We will talk about this differentiation towards the end of this chapter, but for now just assume that single threaded processes, they are the usual process. They have a single chain of commands to execute. Usually these kind of processes, they are easy to handle. They have less issues associated with them. So for now, just assume every process is a single threaded process. Usually, a process has a program counter associated with it. That program counter actually stores the address of the next instruction that this program has to execute. Usually, uh, one process is just a set of instructions. You may you may have an analogy or probably the exact same thing when you write down your C program, a C++ program. Usually you have a set of lines that you want to execute. That is a program. And when you actually execute it, when you are running it, it becomes a process. So now probably you may have a fair enough idea what do we mean by a process, and it only means that it has a set of instructions and they are executed just one after the other in a sequential manner. So it when we load a process or your C++ program onto when we submit it to the operating system, it loads your program onto the RAM, and then it starts executing all the instructions one by one till the end of the program. Once your all the instructions are executed, your program completes its execution, and all the resources that were given initially to this process, they are reclaimed back by the operating system. Usually when we have multi-threaded processes, we have one program counter per thread. But this is something that we will discuss towards the end when we have a bit of good understanding or deeper analysis of what a process actually means, how many stages it has, and what are different components of it. Usually when we are running in a system, so every system, it may have multiple processes running in the system. I'm deliberately not using the word simultaneously because at one time only one process can be running in the CPU. So in the whole system, there can be multiple processes running in the system. There can be one or more users in the system, and then there might be some operating system that is running on your machine. And by this machine, we mean that it may have one CPU, it may have multiple CPUs. It is also possible that those CPUs are working in a synchronous manner or in a symmetric manner or in asymmetric manner. So there are several possibilities when we discuss about process management. Usually when a process is running in the system, there are multiple things that are associated with it. Usually we have a module in the operating system that manages all the process related activities. Usually the responsibility of that module is that it should create the user level processes and corresponding system level processes, and once a process is in the running state in the system, it may suspend some of the processes, resume them, and when there is a contention between multiple processes, it may provide mechanisms for synchronization or message passing between processes, communication between processes. So all of this is the responsibility of this process management module. And once a particular process completes its execution, it is the responsibility of this module to delete this process or to terminate this process and just claim all the resources associated with it. So up till this point in time, we know that it is possible that a process might be running in the system. That is what a process requires, the CPU timing. However, there is an interesting note over here that I want to share it with you. We know that there are two types of sharing. One type of sharing is when, for example, the room light that is switched on, and for example, if you and your sibling are sitting in one room, both of you are sharing the same light, and the receiving of light from one party does not affect the amount of light that is received by the other party. So both of you are enjoying the same light. The same goes true if you and your sibling are watching some game on the television. So you know that both of you can watch that show and without interrupting each other, without affecting the rights of one another. So both of you can watch it simultaneously. This is one way of sharing. That the sharing of a resource by two parties does not affect any of them, and both of the parties and their rights, they remain without any compromise. However, if both of you are sharing a lunch and you are having your half portion, it means that something tangible is actually cut into half uh, and shared by you and your sibling. So there are different types of resources, and some resources can be shared in a way that both of the parties can enjoy that or can use that resource. However, there are resources in which this sharing is not possible. So if you want to hold something, you only hold it yourself. For instance, you have a motor car at your home. So either you can drive it or your sibling can drive it. So not both of these parties can drive it at the same moment. Having said that, your processor is a resource that is of the second type of resource, or its nature is something that it cannot be shared by two processes simultaneously. At any particular time, one process can only be executed in your CPU. And by this, we also mean that if we have multiple processes running in the system, the rest of those processes, they have to wait for some time before before it is their turn to get the execution time. Uh, However, as CPU is quite fast and it can handle multiple instructions or thousands and millions of instructions per second, it switches the time between multiple processes. So we get this feeling that multiple processes are executing in parallel, or uh, parallel is probably a better way than simultaneously, because parallel means that they are in the processor at the same time, and but not exact time. However, simultaneously probably may reflect that they are in the processor at any point in time. All right. So after this discussion, we know that if one process is in the processor, it means that all the other processes that are there in the system and they are waiting for the processor, they are in some queue. So we call all of these processors as ready process. These processes are ready and they are just waiting for the processor to look at them. So you can have this analogy that if you visit some physician, some doctor, and you are there in their waiting lounge. So the doctor is the processor, and the patient that is in his room is a process. So at one point in time, The doctor is consulting one patient or observing one patient, and on the other side, all of the rest of the patients that are waiting in the waiting room, they are in the ready state. They are just waiting that as soon as the processor gets free, they can have their own turn. So at least for now, we know that there are at least two stages or two states a process can be while during its execution. The first one is in the running state, which means that the process is running in the system. It is utilizing the CPU time. And the second one when it is ready, meaning that the CPU has just took it out to accommodate some other process, and this process is waiting for the CPU, for the processor particularly, to get free. So we have two states. The first one is the ready state, and the second one is the running state. On the previous slide, we also had one interesting terminology, and that is interrupt. So when a process moves from a running state to the ready state, we have interrupt. So a process is interrupted. So what is usually interrupt means? So let's take this analogy that you are studying your operating system course, and in the meanwhile you receive a call from your friend, and you by some chance you decide to take that call. Now what you will do, that you were actually studying the course and you stop your studying over there and you move on to receiving a call. So that call is actually an interrupt. So now you will handle that interrupt. You will receive that call for a while, and once you complete it, then you will come back to resume your study. So interrupt is usually an event or that interrupts the usual sequence of a process. So usually when we are working on something, and in the meanwhile we receive a signal that we should stop or current processing right away, and we may have to move to the next process, or we may have to move to handle something important as well. So there are multiple types of interrupts. There are some software interrupts, then we have some hardware interrupts. And I hope you remember that just a while ago we were discussing about nested interrupt handling and sequential interrupt handling. So this interrupt is actually associated with that interrupt handling routines. So we may have uh, hardware interrupts as well as some software interrupts. Hardware interrupts are generated by the CPU, that they may generate some signal, and that is transmitted through the system bus. And the software interrupts, they are usually called by system calls. So uh, in any of these cases, we uh, hold the current execution of our process, whatever we are doing, and we move on to doing something else. So now let's see an example how we have two processes and how they uh, can share the processor. As we know that both of them cannot be in the processor at the same time, so we will see that how they will take turns. So in this example, we have two processes, P1 and P2. And the requirement for the execution for each of these processes is 40 seconds each. And they arrived at the system at 0 time interval. So at any point in the system that we call as 0, so both of these processes, they arrived at the system. So both of them require 40 seconds from the CPU, and the CPU time slice is 10 seconds. Now, this time slice is another important concept, which means that after this time, after these 10 seconds, the CPU will generate an interrupt to signal the process which is in the running state and take it out from the CPU and put it in the ready state, and take the some other process that is waiting in the ready state, take it into the CPU. And in this way, turn by turn, both of these processes, they complete their execution. So now both of these processes, they have arrived in the system at time interval 0, and both of them require 40 seconds to complete their execution, and the time slice for the CPU is 10 seconds. Now let's see how this thing actually works in there. As both of them as both of them arrived at the same time, we can put any one of them in the CPU first, but as this process 1 has a process ID of 1, we just give it preference, but there is no particular reason why it should be given any preference over P2. So over here we have a chart that reflects running and ready state. We have P1 and P2, and both of them arrived at the system at time interval 0 just by due to its process ID 1. We just gave it some advantage and we put it in the running state. And this is P2. It is arrived in the system, but still it is in the ready state for the first 10 seconds of the CPU. So from 0 to 9, P1 in the running state while P2 is in the ready state. Moving on, from time interval 10 to 19, we have P2 in the running state while P1 is in the ready state. So you can see, or you should expect, that over here at time interval precisely just before 10, we would have an interrupt to change the state of both of the processes. So from here, this process was in the processor, it is taken out, and this process is submitted to the processor. There are still some details that are in there, but we will discuss them just in the due course. From time interval 20 to 30, we again have P1 in the running state and P2 in the ready state. So you see, from 0 to 9 we have P1 running and P2 ready. From 10 to 19 we have P1 ready and P2 running. And then from 20 to 29 we have again P1 running and P2 ready. So at this point in time, P1 has elapsed its 10 seconds, and 10 seconds mean 20 seconds, while P2 has elapsed its 10 seconds out of 40. So 20 seconds for P1 are still left, while for P2 30 seconds are still left. So CPU will keep on switching between both of these processes after 10 seconds time slice that is defined for this example. So for the next 10 seconds, P2 is in the running state while P1 is in the ready state. From 40 to 50, P1 is in the running state while P2 is in the ready state. So again over here you can see that P1 has elapsed 30 seconds of its total time, while P2 has elapsed like 20 seconds of its total time. So 10 seconds are still left for P1 and 20 seconds are left for P2. So we are exactly at this stage when this interrupt is about to happen. So now from 50 to 60 we have P1 in ready and P2 in running state. Now you can see that both of them have elapsed their 30 seconds. Now P1 is here, and now it has elapsed all of its 40 seconds, while P2 is here with its 30 seconds. So you can see that over here, before even this interrupt occurs, we may have P1 completing its execution, and the control may be given to the only process that is there in the system, that is P2. So for the next time slot, over here we will not have any process at all, while over here P2 will be in the running state. So you can see over here that we do not have any other process in the processor at this moment, but only P2. So this also raises the question, what will happen if we do not have one process altogether present in the system and we only have this P2? So we will not have this running and ready switching, and this will continue its execution, and it can complete it till here probably. So running, running, and it can complete its execution. Uh, so that is this example. I hope this should be clear. If you have any query, if there is any concept that is not easily understandable, please do write to me. Alright, so now let's have a class exercise to see whether you have grasped these concepts or not. So over here we again have two processes, P1 and P2. However, this time the burst times are a bit different. For P1 it is 30 seconds, for P2 it is 50 seconds, and both of them again arrived at time interval 0. So again you can see that any of these two processes, they can go in the processor first. However, just with the P1, its ID, we will give it a bit priority, and it should go in the processor in the running state before P2. Again, there is no discrimination whether, or there is no reason why P2 cannot go at this stage. However, we are just having a, just for the sake of symmetry between the example, uh, between all the class fellows, and between the codes and on the slides, we may have some unanimity. So let's take this P1, this process ID, as the first process to go in the running state, followed by P2. So let's do this exercise. You have 10 minutes for this. Please stop your lecture over here, complete this exercise, draw a table, put P1 and P2 in running state alternatively, and see how the chart looks. And once you are done, please resume the video then. Please stop it over here right now. Welcome back, students. So I hope that you have some chart with you. So let's see whether it resembles the one that is there on the slides. So for the first 10 seconds from time interval 0 to 9, we have P1 in the running state and P2 in the ready state. Over here we should have an interrupt, and we will have a change in the state of P1 and P2. So let's see. So over here now P1 is in the ready state from 10 to 19, while P2 is in the running state. From 20 to 29, P1 is again in the running state and P2 is in the ready state. So you can see that by this time P1 has elapsed 20 seconds, while P2 has elapsed only 10 seconds of its execution. Moving on, now from 30 to 39, P1 is in the ready while P2 is in the running state. From 40 to 49, you can see that P1 has completed his execution or completed all the 30 seconds that it required, while P2 has only elapsed 20 seconds of its execution, and still because it required 50 seconds to complete its execution, still 30 seconds are left. So over here you can see that we do not have any process in here, so this P2 is in running state. And you will see an interesting phenomenon over here when we will be at time interval 60, because again we will have an interrupt, and we will see whether is there any process in waiting for the processor. So you can see that is as there is no other process in the system, again after the interrupt, the CPU time will be given to P2. Moving on, the same will happen from 70 to 79, that P2 will keep on running, and now it has elapsed all of its 50 seconds. So over here it will terminate the execution as well. There is an interesting point to consider, that at here at 59, at 69, we have that interrupt, and after that interrupt the CPU evaluates whether the same process should go back to the CPU, or is there any other process available in the system that should go in. So for a while we have that interrupt, and again, because there is no other process available in the system, then P2 will continue its execution. So I hope the concept of these running and ready states and with multiple processes, it should be quite clear. In the next class, we will try to add some more details onto them, and we will have some more stages, and we will see what is the total life cycle of a process and various other useful stuff. So that is all for today, students. Thank you. Bye.